Hello, hello. So the next talk is by Jael and Cedric Halbronn about hunting for overlooked cookies, Windows 11 KTM, and baking exploits to them. Have fun.
Hi, I'm Jael. I'm a security researcher at PixiePoint Security, and with me is Cedric Halbronn from EasySec Lab. Today, we'll be talking about the first two vulnerabilities that I discovered in Windows 11 and how we exploited them. But first, why should you care? Well, these two vulnerabilities that I discovered were probably the single biggest reason as to how I got employed in PixiePoint Security, and which is why I'm able to do security research full-time. So if you're new to this industry or looking to break in, I promise you that after this talk, you'll get actionable advice as to how you can find your own vulnerabilities and break into this industry. And for the more advanced researchers in the audience, KTM remains an accessible, complex, yet woefully unaudited attack surface to this day. So I promise you that after this talk, you'll know more than 99% of people about KTM, and you'll be well equipped to kickstart your own research in the future attack surfaces.
Okay, so what is KTM? So KTM stands for Kernel Transaction Manager, and the best way to learn about a component is to ask the developers, right? So KTM has been created in the Vista era, and so we're going to watch a small video, like a 1-minute video by the developers, and they're going to explain to us what is KTM.
All right, so we're in Windows World again, and this is quite a cool office, man. Nice drum set. So that's how you get your stress out.
That was the
late at night coding.
Although you can tell from the dust on it, I've been working a little too hard to play lately.
Okay. So who are you? What's going on?
I'm John Cargill. I'm a developer in the Windows storage team, and I own the Kernel Transaction Manager.
All right.
Which you've probably heard of in
Kernel
relation to the transactional file system and the transactional registry.
Excellent.
So basically, KTM is a kernel component, so it's down below the user kernel boundary. So we actually created 4 new types of OB objects. There's a transaction. Transactions get logged in TMs, which are represented by a log file, and then there are RMs, which are resources that take part in transactions. So every TXF volume is an RM, every registered hide is an RM. And then RMs enlist on transactions. So the state of the relationship between an RM and a transaction is represented by an enlistment object. So those new object types get exposed, and APIs to manipulate those object types.
Excellent.
State machines keep track of the state of all of those things.
Okay, so I think there is something about like being in the developer side and being in the attacker side, and I think in the security industry, most people would say that attackers know better the edge cases of a product because we've been looking at edge cases in order to attack them, right? So let's look at what we get from the reverse engineering and understanding how things work. So yeah, there are 4 different objects that are interesting to talk about. The first one is a transaction manager. And so that's the first object in order for you to talk to KTM. Then there is a resource manager, and the resource manager is about dealing with a resource. So it could be a file system, it could be a registry key, this kind of thing. And then we create a transaction. It's basically the idea of something atomic. And so in order to link the transaction to the resource manager, we create this enlistment, which is basically just here to link an atomic operation to a resource. And so that's what we can call from user land. And so we are interested in attacking the kernel. And so the kernel, on the kernel side, what is KTM? You can think of KTM as basically a series of kernel objects. And in general, that's what the kernel is. It's nothing complicated, it's just kernel structures. And so KTM would be, the KTM structure on the left is the transaction manager. The other ones are self-explanatory. And seeing the relationship between the objects gives us an idea of what the kernel is going to do, because it's going to parse this object and it's going to do things with them. And so a transaction has a linked list of enlistments associated with that transaction. And then the resource manager has a linked list of enlistments that are possibly from different transactions. Okay, so if we look back at what KTM, how it was attacked in the past, I won't go over all the history because most of it is actually not that interesting. But the vulnerability before 2017 were not that interesting from an exploitation point of view and an impact. The vulnerability from 2018 was very interesting because for the first time, there has been an exploit in the wild, exploited in KTM, so in the driver. And it was very interesting because at that time, the browser sandbox were hardened to avoid the Win32k APIs to be reachable because there were lots of bugs, and so to avoid reachable from the sandbox to avoid sandbox escape. And so this bug was targeting KTM, and that was allowed from the sandbox, and it's been exploited in the wild. There are a few bugs in 2023, mostly found by Project Zero in KTM. And early 2024, I had been working on the exploit from 2018. And because there was no public exploit for the bug, and we couldn't find the binary on VirusTotal or anything, so there was no public info on how the exploit actually worked. A colleague of mine and myself decided to write an exploit for it. And so after we wrote the exploit, I decided in 2024 to release a training where the idea was to exploit KTM and develop an exploit for it, or even two different exploits with two different approaches. And the idea was more to focus on the methodology than the actual KTM object, but KTM component, but obviously because it's focused on KTM, you learn a lot about KTM. And so Jael attended this training, and that was at the beginning of early 2024, and at the end of 2024, he found 2 use after freeze. And I was like, how is that possible? So the first thing I guess most people in the security industry agree on, I guess, tell me if you don't agree, I'll be happy to discuss that with you, is be curious. And so, yeah, that's the first tip for people, because you want to know how things work before attacking them. And so when we were doing the research back in 2018, we didn't have a clue what KTM was. There was no public research because everyone was targeting Win32k, and we needed to know a little bit more about the object. So we started reversing the KTM object, and there were like these 4 KTM objects, and each one had a cookie 1, 2, 3, 4. And we didn't reverse more, like the 5, 6, like we didn't revert them.
So earlier last year, I took Cedric's KTM course. While doing it, I came across this table of object cookies. Instantly, my eyes were drawn to cookie 5 and cookie 6, which contained undocumented objects. According to the table, these corresponded to a protocol address information object and a propagate request object, respectively. So I got curious. I did a quick Google search for the value of cookie 5, but I didn't find anything interesting. So I took the KTM driver and I placed it in IDA3, and I did a quick text search for the value of cookie 5. I got one result, TM register protocol address information, and I just started manually reversing the cookie 5 object line by line in assembly this way. Occasionally, I would add little comments about what I thought each line of assembly was doing in each code block. Now, it's worth pointing out that during this time, I wasn't looking for vulnerabilities. I didn't even know if this function was reachable. All I wanted to know was, what do these overlooked cookies do? And I picked this methodology up, the methodology to not look for vulnerabilities upfront, but instead try to deeply understand the underlying component first, from a talk given by Satoshi Tanda, do not find bugs, bugs will find you. And I spent about a week reversing cookie 5 and cookie 6 this way, and when I was done, I just started playing around. Right? I figured out how to reach these functions, and I wrote a little POC to explore the functionality of these objects. Once again, at this time, I wasn't looking for vulnerabilities. I was just merely trying to understand the extent of these objects, as well as the intent behind the programmer who designed these objects. And while doing so, I came across 10 promising ideas for potential vulnerabilities in KTM. Unfortunately, all 10 were failures. Now, you don't have to read this slide, but I've added it because I think it's very important to show what the reality of vulnerability research is really like. It's not very glamorous, and oftentimes it's a lot of repeated failure, rejection, and paranoia. And with each failed idea, it felt like a brick wall, and I grew more and more frustrated. Looking over my notes, I found this diagram I created while I was trying to pinpoint some edge case ref count / race condition vulnerability. And it looks eerily similar to a red string conspiracy diagram. So it's really hard to overstate just how much of a mental game vulnerability research really is. As someone who's seated in this audience just last year, I felt that everyone on stage and everyone in the audience is just simply too good to fail, and they're just so much better than me. But that can't be further from the truth. As everyone on stage can attest, we've all failed more times than we can count. The fact of the matter is, failure in this industry is inevitable. And I'll share something I've never told anyone. This was actually my third time reversing the KTM driver. My first and second times both ended up in failure, and I just never bothered to tell anyone about it. Whenever you're reversing a component, you're constantly being told that your understanding of the code base is wrong. But that's okay, because you only have to be right once. So vulnerability research is a lot like playing baseball with no strikeouts. You can constantly swing in silence until you succeed. And what I found really works is exercising regularly. Late one night while I was running on the elliptical, an idea came to me. What if I freed one object while another object was in use? Initially, I dismissed this idea, but I told myself, I already have 10 failed ideas. What's one more? So I went home and I tried it. And this is my first very own blue screen of death in the Windows kernel. And as you can see from this snippet in my notes, I was so happy when I first found it. So what is the Cookie5 object? The Cookie5 object is a protocol. It's created when you call this NT-register protocol address information ext syscall on a resource manager's handle. This function allocates and initializes the protocol object, and in doing so, it adds the protocol object to the protocol list head linked list of the resource manager. Now, there are really only two important fields in a protocol. The first field is the protocol GUID. Now, this is just a GUID that we supply to the syscall I mentioned, and it's worth pointing out that every protocol has a unique GUID. Now, the next important field is the resource manager field. This is just a pointer to the resource manager that registered the protocol. And finally, there is one interesting kind of protocol known as a promoting protocol. Now, the only difference between a promoting protocol and a normal protocol is that a promoting protocol has this special static GUID that you see here. Now, you don't have to remember this value. All you need to know is that if a protocol has this specific GUID, it's a promoting protocol. Now, let's take a look at cookie 6. Cookie 6 is a propagate request. It's allocated and initialized when a transaction undergoes transaction promotion, which calls this TMP allocate propagate request function. Now, there's only one important field in a propagate request, and that's the resource manager field. However, unlike the protocol object, the resource manager field is initialized to null. So after allocating a propagate request, it's dispatched in this TMP dispatch propagate request function. Let's take a look at that. The first thing that this TMP dispatch propagate request function does is that it finds the promoting protocol. Now, we'll remember that this is just a protocol with that special GUID I mentioned. And the next thing that this function does is that it reads the resource manager field of the promoting protocol, and it will set that value to the resource manager field of the propagate request. Now, can anyone spot the vulnerability here? Correct. After the promoting protocol is found, but before the resource manager field of the promoting protocol is read, we can actually free the promoting protocol in this window. Let's take a look at how we do that. You'll remember that when a resource manager is freed, all entries in the protocol list head linked list of the resource manager are freed as well. So this is done through the TMP close resource manager function, which calls TMP delete protocol on each entry in the protocol list head of the resource manager. Now, this TMP close resource manager function is just the close procedure of the resource manager object, and it's called when we close the user mode handle of the resource manager. What this means is that we can actually free the promoting protocol and then reclaim it with a name pipe to poison the resource manager field of the promoting protocol. So when, in the next step, when TMP dispatch propagate request uses the poisoned resource manager in KE wait for single object and KE release mutex, as well as TMP set notification resource manager, we can get primitives. Now, let's talk about the constraints to reaching this vulnerability. So the first constraint is that the exploit needs to be run on a clustered disk. So the disk that I'm using right now for my laptop is a basic disk. If my laptop crashes, then the availability of that disk goes with it. On the other hand, a clustered disk is a disk configured for availability. It's a disk used in Windows Server environments where it's backed up by multiple nodes. So if one server node crashes, then the availability of that disk still remains, as you can access it from other nodes. Now, this is done through the TMP is clustered transaction manager function, which we will need to call before we trigger the vulnerability. And as you can see, it makes an IOCTL disk is clustered request to the device driver and returns a value. Now, this value needs to be true for us to reach the vulnerability. So I've actually ran this exploit on a clustered disk. This requires you to set up 4 Windows Server VMs and a file disk cluster, and this actually returns true. But when I was debugging this exploit to check if it even was a vulnerability, I patched it with a WinDebug script to just return true, to emulate a clustered disk. The next constraint to reach this vulnerability is that only the KTM RM for Distributed Transaction Coordinator service can register a promoting protocol. Now, this is checked in the NT register protocol address information ext syscall, which checks if we are trying to register specifically a promoting protocol. If we are, then there'll be a call to SEXS check to check if we are running within the security context of a KTM RM service. If we are, then we'll be allowed to register a promoting protocol. Otherwise, we'll just return out of the function. Now, please note that this is a legitimate security boundary, and is the reason why this vulnerability requires high privileges. But when I was trying to even see if it was a vulnerability, I just patched this SEXS check to just return true. Now,
yeah, so now we've got some knowledge about the vulnerable function, and so we basically need to win a race condition while this thread is blocked into this function, and we need to basically free the protocol and reallocate that chunk from another thread before the protocol is actually used by this function. And so, yeah, let's go back to this function and look at all the different places where we could have been able to replace the protocol, free it, and replace it. So there is different places, and let's look at all of them one by one. And we're going to do that assuming we have medium integrity level to get started. So the first option is we are able to free the protocol and reallocate that chunk from the other thread before the set notification resource manager function is called. And the first thing we see inside this function is that actually the resource manager that is passed to this function is going to be retrieving a TM field, and then is going to dereference that field. So we need a valid TM field. The problem is that we control the protocol, but not from the beginning. And so at that stage with the second bubble, we don't control the actual protocol. And so the propagate request resource manager field is actually going to be set to the kernel real resource manager. And so when we reach the very end, it's actually going to use that resource manager. And the reason I say it's going to be SOD is because when we actually try to free the resource manager in order to free the protocol, it's actually underneath. It's not shown in this code source code, but it's going to actually set the TM field to null. And so the TM field set to null from the protocol is going to be inherited by the propagate request. So because it crashes, we can't exploit it. The other thing worth noting is because we were not able to reallocate the protocol earlier, we don't really have any control anyway. So that's not a good option. Second option in this orange block, so it's before the release mutex function. And so here, the first thing we see is that because we control the protocol, it means we control a fake resource manager in userland, and we can have a fake mutex. And so that gives us some control because some function is parsing some data that we control. The first thing we see is that this mutex, in Windows, a certain type of mutex is a mutant, and so they have a current thread field, and we need this to be a valid eThreads pointer. And so because we assume medium integrity level, we can use NT-query system information, which gives us a leak to arbitrary kernel object. So we can set our current thread to the E thread. And the other thing we know from the bugs from 2018 is that KE release mutex is a good function to get an arbitrary write primitive, typically overwriting 0 to any address or incrementing the content of any address. And the other thing we noticed doing the research is that there is a trick we can use in KE release mutex, and most specifically into the function ki try unwait thread, to block indefinitely. And the reason it's interesting is because it allows us to avoid the BSOD that we couldn't avoid for the same reason as before, because we don't control the resource manager being passed to the set notification resource manager. And it's going to dereference a null pointer. And same thing for the yellow blocks. Even though we managed to control the protocol before the wait for single object, we don't get anything out of it. Yeah. And so then the last block, the last option we need to analyze is the one where we are able to control the protocol from the green block, and we are able to do it before the protocol resource manager field is retrieved and set into the propagate request. And the first thing we see is that from now on, because we were able to control the resource manager, the real resource manager in the kernel is still there, but the protocol is controlled with our own data, and so we are able to craft a fake resource manager into the propagate request. And the consequence of that is that we can just craft a fake TM pointer in userland, and it won't be SOD. So that's the best. In practice, when we're testing that, the best we've been able to achieve so far is having control of the protocol in the orange box. So what this means is that we don't control the resource manager early enough. We need to avoid the BSOD. And after leaking the E thread from previously, we can trigger a write primitive and then block indefinitely. So that's a scenario where it's exploitable. OK, so if you haven't been following that much the source code, I'm just going to summarize the exploits so everyone is on the same page with a diagram. So we've got our exploit thread. And in user mode, and we've got in the kernel the structure, the EThread structure, and the NTOS kernel binary. And so the first thing we do, like Jael was explaining, we create a promoting resource manager, and then we register the protocol to that resource manager. Now, we can leak arbitrary addresses in the kernel using the NT-query system information call. So, for example, the EThread structure, and we can use enum device drivers to leak the NTOS base address. Now, we trigger the vulnerable function, and the first thing we do is by triggering the transaction promotion, and the first thing it actually allocates a propagate request structure in the kernel. And now we're trying to win the race condition, so we are freeing the protocol from another thread by closing the handle to the resource manager, and it's going to end up closing the protocol and freeing it. But as we saw that we are only able to reallocate, to free that protocol from the orange block, it means the propagation request resource manager field is going to be set to the same as the protocol. It's going to end up deleting the protocol. And now from another thread, concurrently, we spray name pipe data in order to replace the protocol with a fake protocol. And we can have this fake protocol fields to point to certain kernel fake object in userland. And now we can use the leaked addresses to basically craft certain fields in this fake kernel object in userland to get a write primitive. So like I said earlier, we can either use a 0 overwrite or an increment. And finally, we can block indefinitely to avoid the crash in the last function. So let's zoom a little bit at the two primitives. So the first primitive is a 0 overwrite. On Windows, there is a previous mode field in the E thread, which dictates if you're basically a thread in user mode or in kernel mode, and it's used basically to check in the kernel if you're able to call certain APIs. And so if we set previous mode to 0, it means our thread is basically like a kernel thread, and we can basically call certain syscalls from userland, like NT-read virtual memory or NT-write virtual memory, passing kernel addresses, and it will be allowed. So that's a trick that's been used. The problem is that to use this trick, basically, the idea is we set previous mode to 0, and then we need to go back to userland, because then our own thread has kernel God mode permission, but we need to go back to userland, so then we can actually call the anti-query, anti-read virtual memory and anti-write virtual memory to get the arbitrary read-write. But here we have the constraint of being blocked indefinitely into the kernel, so our thread is never going to go back to userland, so we are never going to be able to call these functions. But basically what we can do is we don't need necessarily to use our own thread. We can use another thread, and then we don't have that problem anymore, because that thread never goes into the kernel. It's always in userland. We just change this other thread previous mode, and then that's fine. That's the first option. The second option is to use the increment, and for instance, targeting the SE debug privilege flag inside NTOS kernel, and by incrementing it by 3. Back in 2018, the primitives did exist. The increment we've been using is a different one, because in the exploit from 2018, you could trigger the KE release mutex many times, but here we can only do it once. So we found a way to basically chain increment with only one call to KE release mutex. So now we have a small demo. We had 2 options, either setting up a cluster disk and 4 virtual machines, find a 0-day in KTM RM, or use 2 WinDBG commands. So I'll let you guess which one option we've chosen.
So we'll be running as a medium integrity shell on the latest version of Windows 11 with this vulnerability. Now I'll zoom this in. Okay. I'll use 2 WinDebug commands. I'll use 2 WinDebug commands to. This first one will patch the IOCTL disk is clustered request to return true to emulate a clustered disk, and this WinDebug command will patch the SE access check to return true to emulate a KTM RM service. So let's run it. Oh, yep. Okay. And as you can see, we've achieved system privileges.
Okay, so we've got an exploit like with medium integrity level, and also relying on this service, which is high privileges. Let's look at how we would actually build an exploit for low integrity level. And it needs a little bit more of engineering. So if we go back to this function, the first thing we need is basically we need to win the race earlier. And the reason is because we need to abuse KE word for single object, because we don't have any other way to leak a kernel pointer, and this would allow us to leak, to trigger KE word for single object by crafting a fake resource manager field from the protocol we control, and pass a fake mutex to KE word for single object. And so it's known from the same bugs, from the bugs I was talking about from 2018, that KE wait for single object will basically add our thread structure into the thread waiting to basically acquire the lock. And so it's going to write the thread pointer inside the mutex linked list, and we can potentially read it from userland. But in order to read it from userland, because it's going to continue executing the code, and it's going to basically call release mutex and remove the thread, basically, we need it to temporarily block. But KE wait for single object is a function that is supposed to block waiting for a mutex, so there is a piece of code in there that should be possible to block. Assuming we've blocked into KE wait for single object, we can leak the thread pointer from userland, and now we can unblock the thread by changing the structure from userland, because they are all fake. And now we can let it go, and same as before, we trigger a write primitive in KE release mutex. So here we have 2 options, the 0 primitive, the write 0, or the increment. And the most obvious one is to use the 0 override, because we only have leaked the thread, so we don't know where the NTOS kernel is, and we can just override the thread previous mode field with 0. And here we can't just block here because, like I explained earlier, we've changed our isRed previous mode. And so if we want to abuse that primitive, we need to go back to userland so we can actually call the syscalls NT-read virtual memory and NT-write virtual memory. So we need this to return. We can't just block. And that's where actually we can't, that's because we need the valid pointer same as before. And so that's why we can't actually just rely on winning the race from the yellow block, because we need to control the protocol resource manager from the green block in order for the propagate request resource manager to also be controlled to avoid the crash in the last function. And we still also need a 0-day inside that service. So the next thing I want to talk about is how did they patch it. So we know it's a race condition, it's a use after free. The way they patched it is basically they made sure that there is no way to free the protocol before the resource manager field. Oops. All good. Okay. They made sure that you can't actually free the protocol before they retrieve the resource manager field from the protocol. And also they make sure that the resource manager field is only fetched once. Because if we go back here, you can see that the protocol resource manager is fetched many times. So now by doing this, you can't acquire the mutex before the resource manager field is retrieved, and that should be good. Looks sane. Yeah. Oops.
Now, at this point, I was all smiles, right? Like, I had found a bug, or rather, a bug had found me, and I was ready to move on. However, when I told my friend about this, he asked, why was I moving on when I hadn't audited the rest of the KTM driver? So I told him there were 3 reasons, right? The first reason is that I thought I just got lucky, right? No one thought to look at these objects, and that, honestly, it's not real vulnerability, right? You have to be some crazy KTM RM service, and you have to be running in some crazy Windows Server environment. And lastly, that people smarter than me have probably audited the rest of the driver already. But I would caution you to not, and frankly, I thought that my submission, I was frankly surprised that Microsoft even accepted my submission, and I was ready to just take the money and run. But I would frankly caution you to not let your biases hinder you, right? So the criticism that I just got lucky and that no one thought to look at these objects, it's actually a compliment, right? That I have this skill to find stuff that people overlook, right? The whole point of offensive security is to look for what? Look for vulnerabilities in places where people overlook. So having this skill to pinpoint what others might miss is an asset, and that I should be searching for other places to use this skill. And maybe they weren't real vulnerabilities, right? Sure. But I still got real benefits from it. I got $2,000 from Microsoft for reporting it. I got a job at Pixie Point Security, and supposedly I'm an OffensiveCon speaker. So I really hope my talk later goes well. And thank you. And perhaps most insidiously of all, that smarter people have probably audited the rest of the driver already, right? Remember, there's no penalties for trying. You can swing in silence as long as you want until you get a home run. And from what I've learned, different researchers like to find different vulnerabilities. So the truth of the matter is that most code is rarely audited in real depth. I'm glad I had that coffee with my friend because he encouraged me to continue on, and so I did. Now we'll remember that when we run my exploit on a clustered disk, we end up dispatching a propagate request. What happens if you run my exploit on a basic disk? Well, you end up migrating an enlistment. Now let's take a look at the IDA graph view of the function that migrates enlistments. It's about 50 lines of C code and roughly about 7 code blocks wide. And when I saw this, I knew there was an issue, right? Let's think about how we would implement a function that migrates enlistments. So if it were up to me, I would first lock the mutex of the enlistment I was migrating. I would lock the mutex of the transaction I was migrating from. Then I would lock the mutex of the transaction I was migrating to. So that's the destination transaction. I would perform the enlistment migration, and then I would release all the mutexes I acquired. Now, any guesses for how you think the KTM driver implemented enlistment migration? Correct, they just migrated directly. I guess this function had a license to UAF because it was 0 locks, 0 security, 7 code blocks long. Let's take a look at the TMP migrate enlistments function. The first thing it does is that it reads the enlistment from the enlistment head linked list of the source transaction. Then, it swaps the transaction field of the current enlistment from source transaction to destination transaction. Next, it's going to verify the list integrity of the next same transaction linked list of the current enlistment. And if that is valid, it's going to remove that enlistment from that linked list. Finally, it's going to verify the list integrity of the enlistment head linked list of the destination transaction. And if that is valid, it will add the current enlistment to that linked list. So you can see from a high level how it's actually migrating the enlistment from one transaction to another. Now, can anyone spot the vulnerability here? Correct. After the transaction field of the enlistment is swapped from source transaction to destination transaction, but before the next same transaction linked list is verified, we can actually free the enlistment in this window and reclaim it with a fake enlistment. So the fake enlistment gets added to the enlistment head linked list of the destination transaction. Now, it's actually not exactly clear why we can free the enlistment in this window. So let's talk about how we typically free enlistments. Traditionally, and this was done in the 2018 exploit, we free an enlistment by committing a prepared enlistment. What this means is that we call commit complete on an enlistment handle, which ends up calling this TMP process notification response function, and which calls this TMP finalize enlistment function. Once that's done, all we need to do is close the enlistment's user mode handle with close handle, and then we're able to free it. Now, if we try to free an enlistment any time it's used in the KTM driver, it won't work. So why is there a vulnerability here? The vulnerability exists because in TMP migrate enlistments, the destination transaction's mutex is never held. This means that when we call commit complete on the enlistment handle, which ends up calling TMP process notification response, the first thing that this function does is that it acquires the mutex of the transaction the enlistment belongs to. So in effect, the thread safety of an enlistment is protected by the transaction's mutex that it belongs to being held. So if we try to call commit complete on an enlistment anywhere else, the transaction that the enlistment belongs to is always being held, so we'll never be able to free it. The one exception is in TMP migrate enlistments, where the transaction field itself is swapped to destination transaction, and that does not have its mutex held. So we can call commit complete in another thread during TMP migrate enlistments to free the enlistment. So let's try that. And when we do, it does not work. Why? Well, it turns out that only committed transactions can free enlistments. What this means is that we'll have to call commit transaction or commit transaction async on the handle of destination transaction before we can free the enlistment this way. But we don't have the handle to destination transaction. It's a kernel mode transaction created internally, and we never get a user mode handle to it. So the traditional way of freeing enlistments does not work in this case. And when I realized this, I was furious, right? I found the vulnerability in like 10 minutes, but for the life of me, I could not get it to exploit. And this got me thinking, is this even a real vulnerability? So I thought about it some more. It seems objectively weird that I'm not able to free an enlistment before committing a transaction. It's like if you had rotten ingredients in your kitchen, but instead of throwing it out directly, you had to cook a whole meal with the rotten ingredients and throw out the whole dish. So I thought that the smart minds at Microsoft must have thought of a way to deal with this situation. And as I thought about it even more, I was like, okay, you know what? I'm just going to try every function in the KTM DLL, and hopefully one works. And I tried all of them except one, and nothing worked. Except for this one. So this function is called read-only enlistment, and basically it says it's going to convert a normal enlistment to a read-only enlistment. Now, initially I dismissed this idea because I'm trying to delete an enlistment. I'm not trying to convert it. But I was like, this function can't stop me because I can't read. So I called it anyway, and it's actually exactly what we need, right? It allows us to free an enlistment before committing a transaction. Now, as you can see from this snippet in my notes, I'm not as ecstatic as I was on the first time, but I'm still very happy nonetheless. So to reach this bug, there are no constraints. You don't have to be a KTM RM service account, or you don't have to run in a Windows server environment on a clustered disk. But because the race window is so small, roughly about 40 assembly instructions, I wasn't able to write an exploit that reliably wins this race. So when I was trying to check if this was a real vulnerability and win the race, I ended up using a WinDebug script that inserts an infinite jump in the race window of the TMP migrate enlistments. So I would be able to force a race win by calling read-only enlistment while the thread was blocked in this while loop. And then I would unpatch that infinite jump with my win debug script and then force a race win. Oh, sorry. Yep, so now I'll show the demo. And 1 second. So once again, we are running in this. It's the same virtual machine. Okay, and then I'm going to break. Yep, so I'm going to, so it's a medium integrity shell in the latest version of Windows 11 that has this exploit. I'm going to use this win debug script to patch the TMP migrate enlistments to force a race win. Basically, once again, I'm adding that while loop in the race window. And okay, then I'll run the exploit. And as you can see here, we've blocked at the while loop in the race window of TMP migrate enlistment. Now I'm going to free the enlistment with read-only enlistment and reclaim it. Then I'm going to unpatch. I'm going to remove that while loop to force a race win. And as you can see, we have achieved the system shell.
Okay, so let's look at the exploitation for this vulnerability. Well, no, actually, we won't have time because otherwise you'll stay there for 2 hours. So let's go with the rest. Oops. So let's take a step back and look at what is KTM from an attacker point of view for the future and more generally for the Windows kernel. So KTM used to be accessible in Sandbox, but recently it's been removed from the Chrome and Edge Sandbox, and it's still available in Firefox. And the way it's implemented, so this is like a commit from the Chrome source code, and the idea is they basically implemented this by relying on something called the Windows component filter mitigation, which is basically an API provided by Microsoft to allow blocking access to certain APIs. So the way it's implemented is this is code from the Chrome source code. The idea is when the process starts, you can basically register your process to support this component filter, which is provided by Windows. And the way it's implemented, so this is code from NTOS kernel, the Windows kernel. It's an API that basically checks your current process disable component, and if it's disabled, then it will just return false. And so, and the way it's used, so this is like 7 functions from the KTM driver. And so all of these functions, at the beginning of this function, they will be calling this API I've showed on top. And if the component is disabled, in this case, the transaction manager component, they will just exit with an error. So you won't be able to trigger these syscalls from username. So that's great. Just noting that it's only 7 functions. So if you want to call create transaction, for instance, you'll be able to do so because it doesn't rely on any handle, so you would typically be able to do that. That being said, we wouldn't be able to trigger any of the bugs that we presented today because in order to do real stuff with real transaction, you need to create a transaction manager, and the ones that are blocked are basically those that you need to create a transaction manager. Okay, so now is KTM safe? So we saw that in 2018 there was this bug. Now we found new attack surface relying on the KTM RM service. So I guess the question is, could we find bugs in KTM RM service? That would be the next thing to look at. Then there is something there are two components, which is transactional file system and transactional registry, which are basically relying on KTM to implement and give APIs, transacted APIs, to avoid having to implement it yourself. So that's a new attack, another attack surface. There is an MSDTC service, which is another service, and there is something called AllETX. So if we look at the transactional registry, this is from the Project Zero bug tracker. There have been a few bugs in the transactional registry. So most of them are security issues. There hasn't been any full exploit that gives you like a shell, as far as I know, but there are interesting bugs. In the transactional file system, as far as we know, there is no public vulnerability, which is interesting, especially because a presentation from the Storage Developer Conference said that the transactional file system is a big attack surface, and just loading the NTFS driver and looking for TXF for transactional file system, we see that there are like 400 functions, so that looks like an interesting thing to look at. Then there is this MSDTC.exe service, which is basically a service in New Zealand implemented with COM APIs. And what is really interesting is that they basically have completely different code for dealing with resources, transactions, totally different attack surface than KTM. And then there is something called AllETX, which is basically a protocol. You're supposed to be able to talk to the MSDTC connection manager, and it's like a 500 pages specification, and you have loads of these structures defined, like loads, as you can imagine, on the 500 pages with like variable size fields, and so, yeah, what could possibly go wrong with this kind of thing? Okay, so in our presentation, we showed that we abuse it's possible to abuse PreviousMode by overwriting it with 0. And so it's because in the Windows 11 version we targeted, which is 23H2, because 24H2 wasn't released when we were exploiting the vulnerability. And so it didn't impact 24H2. And so in 24H2, they enforced PreviousMode to be reset at every syscall. So this is like the KI system service user. This is like the syscall dispatcher. And we see that it does a move to the PreviousMode to be user mode. So even though you are able to, even if you are able to overwrite a PreviousMode, the next time you call a syscall like NT-read virtual memory or NT-write virtual memory, it's going to basically reset your PreviousMode to user mode instead of kernel, user mode being 1. And so you won't be able to abuse it because it's not going to let you read or write kernel memory. But we see that for everything underneath 23H2, PreviousMode is still possible. And I think it's worth mentioning that this is like a big, it may not feel like a big move from the Windows perspective, but this is actually very interesting and very powerful to block this kind of thing, because PreviousMode was a very powerful method, and so it definitely raises the bar for the attackers. This is just to show what happens if you actually try to change PreviousMode to a thread that is in the kernel, and then that goes back into userland. It will actually create a BSOD. It's just worth mentioning that it's not really a security feature, even though it actually is, but it's more important, like the thing that is done when the syscall enters is more important, because you could change an E-thread PreviousMode for a syscall that never is that is not in the kernel, so it won't trigger a BSOD at that stage.
Now, if there's one thing you take away from this presentation, is that I believe you can find vulnerabilities. Thank you. And it's my honor to open the floor to questions. We have a little surprise. Please ask us a question and find us after the talk for an exclusive autographed Magic the Gathering card by both of us. Thank you.
I just want to say that Jael is really good with cards, and when he attended my training, he came to me and he was like, can you autograph me and I give you my card and everything? And he was like, I'm going to do some research in KTM. Yeah. And he did it, and then 6 months later he came to me and he was like, I find vulnerabilities. I was like, that's cool.
Oh no, no cards.
Any question? We've got 5 minutes.
What technique would you recommend if you were to tried to exploit something and you weren't able to use the previous mode technique, what would your override target be?
So the question is, what would you overwrite if you can't use previous mode anymore? Well, that's a good question. And I think the answer it depends what primitive you have. It depends on the context. So we showed the SE debug privilege that we use, but it's very dependent on the context. And you might find other things that are just specific to the bug you're exploiting. Yeah. So that really depends. But yeah.
Just to add on to what Cedric said, I think it would be most dependent on what kind of info leak you have. So if you're from a low integrity standpoint and you have no, like you can't call anti-query system information to leak an E-thread, right? It depends on what info leak you have, right? Now that Microsoft has patched anti-query system information to require SE debug privilege, whenever you're trying to exploit from medium or low integrity, it's basically the same thing. You don't have that info leak. So you need to find another bug or a type of vulnerability that doesn't require an info leak. So we've given the example of incrementing that SE debug privilege global variable 3 times. That would require an anti-OS kernel leak. But if you could leak maybe a name pipe, you can corrupt that data structure to get an arbitrary read write, and that's still not patched. So that's by design, actually. Yeah.
You need additional bugs. You need additional time.
Thank you for your question.
Any other question?
Okay.
So you'll get a card.
Well, if there's no question, we'll be around the talk. I will be around the conference the entire time. So thank you so much.
Thank you.